Welcome everybody to your weekly dose of abstract algebra. This is the first video in a hopefully long series of videos introducing you to some basic concepts of abstract algebra. This is supposed to be a really friendly introduction to these concepts so that even absolute beginners can get a good grasp of the basic concepts. Our starting point is one of the most basic yet very important algebraic structures. We start with the concept of a group. And before we really dive into the abstract ideas and definitions, I want to show you in the first few videos how groups actually arise naturally. And before we get lost in all the details here, let me give you a quick overview of what you're about to learn in this video. We're actually starting with something very concrete, namely this equilateral triangle, and are going to play around with this triangle a bit. And we will discover that there are certain movements called symmetries that leave this triangle unchanged, at least the outer form of the triangle. We will determine all the symmetries of this object, and then I will explain to you how you can take two of these objects and get another one of these symmetries by composition. If you have never heard of the concept of composition of maps before, don't worry, I'm going to give you a very easy to follow introduction to what composition is. Then we are going to find out that the composition on this set of symmetries of this triangle satisfies certain rules. And then we are going to define that a set together with a composition rule that satisfies certain rules or axioms is called a group. This is what this introductory video is about. All right, let's get started by taking a closer look at the symmetries of this triangle. So, let's take a look at this simple geometric object, an equilateral triangle. Angles are 60 degrees, all the sides have the same length. Now you blink for a second and then look again. What happened? Let's do it again. You blink for a second and then we take another look. Nothing happened, right? Wrong. To show you what actually happened, we take a look at the slow motion. So did you see that? I actually rotated the triangle by 120 degrees, but it's impossible for you to detect if you didn't watch the slow motion. And this is what we call a symmetry of the triangle. Let's call it a movement or motion, no need to define it in more mathematical terms, that cannot be detected. Meaning the triangle looks after the movement or motion exactly the same as before. Like this here would not be a symmetry of the triangle, or this here, right? It has to look exactly the same so that if you close your eyes and open them, you cannot detect if any such movement happened or not. This is a symmetry, all right? Okay, to better understand what happens here, I have labeled the vertices 1, 2, 3, and I have drawn these symmetry axes of the triangle. And now it is obvious what happens even if you didn't catch a glimpse of what I was doing. Vertex 1 went to where vertex 2 was, vertex 2 went to where vertex 3 was, and 3 goes to where vertex 1 was sitting before I applied the symmetry. So rotating the triangle about its center point here, center of mass or whatever you want to call it, by 120 degrees gives me a symmetry. If I rotate by another 120 degrees, I again have the same triangle. So this again is a symmetry. So if we start with this triangle and rotate it not by 120 but 240 degrees, this again is a symmetry because obviously the triangle stays the same, only the labeling of the vertices has changed. If I rotate again by 120 degrees, I end up with the triangle I started with. So rotating by 360 degrees is obviously a symmetry, but it's the same as just leaving the triangle as it is. This is called the identity or the identical symmetry. This seems trivial, but will be very important later on that we have such an identical symmetry. So far we have found 3 symmetries of this triangle here. What else could we do? Well, we could take this blue symmetry axis and then flip the triangle about this axis. And then we end up with the same form of the triangle in the same position, only these 2 vertices have changed places. If I flip again, I end up with the triangle I started with, so applying this symmetry 2 times gives me again the identity or the identical symmetry. And of course I could flip about the other 2 axes, giving me 3 different symmetries. Those are obviously different from the rotational symmetries because I cannot achieve this here, interchanging these 2 and leaving this in its place by rotating the triangle, okay? So altogether we have found 6 symmetries of this equilateral triangle. Can there be more? Well, no, because for this vertex I have only 3 possible places, namely it stays where it is, or it goes here or here. Then the second vertex has only 2 possibilities left, giving me 3 times 2, 6 different placements of the vertices 1 and 2. And the place of vertex 3 is of course already determined. If I have chosen places for 1 and 2, then 3 must go in the remaining vertex. So there are only 6 different possibilities of rearranging these vertices, and actually all of them correspond to a symmetry. So I have found 6 different movements that we call symmetries that leave the triangle as it is in its outer form. All right? Okay. Here we have it. The set of all these 6 different symmetries of the equilateral triangle will be called D sub 3. Why D? Because later on we will call this the dihedral group. Di meaning 2, and hedral means this object here has 2 sides. Not those sides, but those 2 sides. I'm not sure about the English term for that, but this is the origin of the symbol D. What do we have? We have the identity, which does nothing to the triangle. Then we have R1. This rotates the triangle by 120 degrees counterclockwise and about the center here of this triangle. And R2 rotates by 240 degrees. And if you wish, you could call the identity R3 because then you have rotated by 360 degrees. But obviously this is not really a rotation. And then we have the 3 reflections which flip about the 3 different symmetry axes of the triangle. If you're wondering about the symbol S, well, rotation and reflection starts with the same letter. I took it from the German term Spiegelung, which starts with an S. That's why I call them small s 1, 2, 3. But of course it doesn't really matter how I call them. This is the set of all 6 symmetries of this triangle. So far this is nothing exciting and has nothing to do with algebra whatsoever. Now comes the important observation. I can compose 2 of those elements, meaning, this is how we write this, R1 composed with S1, this is a little hollow circle, the symbol for composition of maps, if you have heard about that before. If not, that's okay, we're going to discuss this here in detail. This means, beware, we read from right to left, so this means apply S1 first. So flip about this axis here and then rotate by 120 degrees. So we do that here. Okay, so first we reflect about this axis here, then those two switch places here, and then, so like that, and then I rotate by 120 degrees and I end up with this triangle. And now the important observation is composing two symmetries gives me another symmetry, because from here to here the outer form of the triangle hasn't changed at all. So the composition of those two is again a symmetry. Which one is it? Well, take a look at those two. Vertex 3 stays where it is, and 1 and 2 change places. So this from here to here is nothing but flipping about this axis, or reflecting about this axis. So this composition of those two gives me S3, the reflection about symmetry axis number 3, and this is again an element of D3. Well, it is kind of obvious that we end up with a symmetry, because this guy here doesn't change the outer form of the triangle, and this guy doesn't either. So the composition also doesn't change the outer form of the triangle. So let's try it again. S2 composed with R1. If this is all new to you, I would recommend that you pause the video and think about what kind of symmetry this composition will give you. Okay, let's do this together. Sorry, I forgot to mention one important fact. So we start by applying rotation R1, which gives us this triangle. And now S2 is not reflecting about this axis where vertex 2 now is, but reflecting always about the symmetry axis in the original position. I should have mentioned that before, I'm sorry. So we reflect the triangle about this symmetry axis. That means one stays where it is and those two switch places. Now if you compare these two, or those two, you have exactly the same as before. This composition has the same effect as flipping about this axis. So this is interesting because those are two obviously different possibilities to end up with S3. The main point is composing two elements of this set always gives me another element of this set. We say this set is closed under composition. So composing two elements doesn't lead me outside of this set. This is very important. Okay, let's write down some observations. As we have explained here, this set is closed under composition. This means composing is a so-called inner operation on this set. It does not lead outside of this set. Then in general, composing maps is always associative, meaning in such a double composition, it is not important in which order the parentheses here are, so we can drop them all together. This is not really easy to motivate why this should be important, especially because we're so used to it. Like for example, if you have 3 times 2 times 4, this is of course the same as 3 times 2 times 4. So multiplication of ordinary numbers is associative, and actually all the compositions you have met in high school are associative, with the exception of the so-called cross product, if you learned it in geometry, which is very interesting because it gives three-dimensional space the structure of a so-called Lie algebra. So there are actually non-associative operations, but we want to have associativity here, mostly for subtle reasons in proofs. We need associativity, but do not worry about that too much. It's just an important property of composition. Like for example here, again, if you're a complete beginner, please pause the video and convince yourself that this double composition here is actually the same as this. All right, so to prove this, you first take a look at this composition in the first, in these parentheses here, you compose S2 with R1. Now do not jump to conclusions that you have already done that, because as we will see later, this operation here is non-commutative. You cannot simply interchange and get the same result. So let's do this. We flip about axis 2, so we get this, and then we rotate the triangle by 120 degrees. We end up with this triangle. This is the same as flipping about this axis here. So this here is S1. Now S1 composed with itself is clearly the identity. Why? Because if I flip about this axis and then I flip again, well, I end up with the same triangle. So the left-hand side is simply the identical symmetry. What about the right-hand side? Here we have to take our first look at this composition, because we have these parentheses here now. So first, remember, from right to left, apply S1. So you flip the triangle about the first symmetry axis, and now you flip about symmetry axis number 2. Remember, this is not this one here, but the symmetry axis where vertex 2 used to be. So you flip about this axis here. What do you end up with? Well, vertex 1 has gone here, vertex 2 has gone there, and vertex 3 has gone there. So this is actually, so this composition is actually the rotation by 240 degrees. Now if I compose the rotation by 120 degrees with the rotation by 240 degrees, I actually end up with the identity. So these here are actually the same. Now if you're thinking, well, this is pretty tedious, I do not want to do this for all the possible combinations here. This is actually a general statement that composition of maps is always associative. We're actually, or you are actually going to prove that on problem set number 1. So whenever the operation on this set is composition of maps, you never have to worry about associativity. This is always guaranteed. But still, this was again a nice exercise in composing symmetries. So then, also almost trivial, there is a neutral, so-called neutral element in this set. This is the identical transformation or symmetry, meaning if I compose this with any other element, and this is important, doesn't matter in which order, the element stays the same. Well, this is clear because if I apply the identity, nothing happens, and then if I apply this symmetry, I have the same result as applying the symmetry in the first place. The same here, if I apply the symmetry, for example rotation, and then leave the triangle unchanged, I of course also get the same result as simply applying this symmetry. So we have an associative operation, there's a neutral element, and then the most important observation is that every action of an element D in D3 can be undone or reversed, meaning there is a so-called inverse element that reverses the action of the element that I considered. For example, if I rotate by 240 degrees, this is this symmetry, and then rotate again by 120 degrees, so I apply this symmetry, I end up with the triangle I started with. So this composition gives me the identity. And also the other way around, if I rotate by 120 degrees first and then by 240 degrees, nothing has changed. So those two compositions give me the identity, this neutral element that I've established here. And we write this as this element to the power of -1, read R2 inverse, is R1, because R1 undoes the action of R2. And obviously every element has such an inverse. What is the inverse of a reflection? Well, it is the reflection itself, because if I reflect 2 times, I end up with the same triangle that I started with. And now I have established what is called an algebraic structure. Not only do I have a set with elements, but I have an operation on this set, and this operation, in this case composition, satisfies certain rules, which are also called axioms. And what we have written down here so easily and in a compact form took mathematicians a long time until they realized, well, this is a recurring structure. In a lot of different places of math, I have a set with an operation that satisfies these axioms or rules. And this is what they came to call a group. This is one of the easiest but most important algebraic structures. So to wrap it up, let's summarize what we have found. This here I call the conclusion of all this, or it's actually a new definition. We have as a set D3, the set of all symmetries of an equilateral triangle, together with an operation, in this case composition of maps, and this here is called a group, which means the following. First of all, this set is closed under this operation composition, as we explained here. And the following 3 axioms must hold. Axiom number 1, this operation here must be associative, meaning that no matter where the parentheses here are, these expressions are the same. This is true because composition is always associative. And we saw that here in a special case, in an example. Then we must have a neutral element. This is obviously the identical transformation or symmetry of the triangle, which does nothing. So this symmetry that does this nothing at all. Being neutral with respect to this operation means the following. If I take any element, this here is an abbreviation for all. This reversed A means for all. I forgot to mention that here. No matter which element of this set I take, if I compose it with a neutral element, then this element remains unchanged, no matter if I compose it this way or the other way. This is group axiom number 2, and group axiom number 3. Every element in this set must have an inverse element. Here's the notation, d to the power of -1, or just d inverse, such that when I compose d with its inverse, I end up with the neutral element, and also the other way around. If I compose the inverse with this element, then I end up with the identity. Any set with such an operation, such that these 3 axioms are fulfilled, is called a group. And as I said before, this turns out to be, of course, one of the easiest or most basic algebraic structures, nevertheless one of the most important algebraic structures. Now when we deal with numbers, we are used to the rule of commutativity. For example, 3 times 4 is the same as 4 times 3. This is not true here in this group. For example, R1 composed with S2 is not the same as S2 composed with R1. We already found out that S2 composed with R1 is S3, the symmetry reflecting about this axis. One last time, let's take a look at this composition here. First, we apply the reflection about this axis, giving me this triangle, and then I rotate by 120 degrees, and I end up with this triangle. And this here has the same effect as reflecting about the symmetry axis number 1. 2 and 3 have switched places. So this here is S1, whereas this composition is as 3, so they are not equal. And when the law of commutativity fails, we call this a non-commutative group or a non-Abelian group. To honor Niels Henrik Abel, a Norwegian prodigy who died much too early, who was one of the founding fathers of group theory. We are going to hear more about him as this course here progresses. So it is not necessarily true that a group is commutative. Easy example is this group here, D3 with composition. All right, that's it. This concludes our first lesson of week 1 of a friendly introduction to abstract algebra. I'm not sure yet if I'm going to make 2 videos out of these or if I leave it as 1 video. Still trying to find my groove. Would be very helpful for me if you would write a comment below, and of course like and subscribe if you found this video here helpful. Please do not forget, this is really aimed at beginners. So if you already know about abstract algebra or groups, then this of course was all trivial and much too long, but bear with me as we move along. The material will get more advanced. But these videos, especially the first ones, are really intended mainly for beginners so that they have a chance to get used to all this stuff here in a friendly and slow manner. I would strongly encourage you to really do the exercises in problem set 1. Link is in the description. Solution video will be available some days after this year. Yeah, if you really want to acquire a working knowledge of this stuff, then there's no alternative to really doing the exercises on your own. Otherwise, I think it's really hard to get comfortable with all this stuff. All right, if you found this video helpful and if you would like this series to continue for some time, please like, subscribe, share this video, drop a comment below. I would really appreciate that, and I hope to see you soon. Bye bye.